Hello. Jed mentioned in the previous video that a population is a group of individuals of the same species in the same place at the same time. And he used the example of pronghorn antelope. Today, we're going to be building a simple population model featuring pronghorn antelopes. And we'll evaluate whether our model really reflects the pronghorn population or not. Remember, a population can change over time. They can increase, they can decrease, or they can remain stable. If they're increasing, they can be adding more individuals than are exiting the population, and they can add individuals either through birth or immigration. And if they're decreasing, it means they're losing more individuals than they're gaining. And individuals can be lost through either death or immigration. In this video, we're going to keep our population really simple, and we're going to think about only adding individuals through birth and losing individuals through death. So our key inputs then are the birth rate and the death rate, and we're going to enter those in cells B2 and C2. And Jed alluded to these in lecture and gave us the following numbers. He said 1.4 was the birth rate and 1.3 was the death rate. Now here's something I want to point out right away. These are rates. These pertain to a population. We all know that an individual cannot have 1.4 offspring, and an individual cannot have 1.3 deaths. These are rates, and we're going to be talking about how we think about these rates as we build our model. We're going to build a model that considers 20 years of growth, or 20 different time steps. Actually 21. The very first time step is labeled 0, and we'll begin our series and stretch this down to the number 20. Then we're going to start our population with a particular number of individuals, and if we started off with 100 individuals, we'd enter it right here. This is called NT, and at time step 0, this means that we have 100 individuals. Now our model will include equations that are entered in cell B8 that will take the birth and death rate and compute what NT is at time step number 1. That's our goal. Before I forget to say this, I use the convention of using and highlighting my cells in green when I know that they are an entry where I can enter a number into these cells and the rest of the spreadsheet is computed. Now let's talk a little bit about what this kind of population growth model is. We mentioned that it has these time steps, and these are discrete time steps. And when you think about a discrete time step, you might imagine opening up a window at a particular point in time, counting the individuals that are there, in this case pronghorn, and then closing that window up. So if these time steps represent years, then we might say that we're going to do a population census, let's just say in the middle of the summer. We open up the window, we count our pronghorn, we close the window, and then we come back 1 year later and we open up that window again. And in between those two discrete time periods, there's a lot of things happening. Individuals are being born and individuals die. And one of the most important things you need to do when you start to build a model is to think about the timing of when these events occur, because we have this discrete nature for our model. So in order for us to calculate the number of individuals at time step 1, we're going to open the window, see that there's 100 individuals there, and then we're going to close the window. Then right after the window is closed, we're going to assume that these individuals give birth. So we're going to count the number of births, and Jed indicated that that was designated with a capital letter B. Here we need an equation that would count the number of births. What would it be? Yep, it's just going to be the number of individuals that we just counted multiplied by the per capita birth rate. And we're going to anchor the reference to cell B3 by pressing the F4 key. And that means that as we drag this formula down the column, the B7 reference will float down with it, but will always be referring to the birth rate that's stored in cell B3. Now, right away, in adding that equation, we've made another very big assumption. What is it? Well, if you've been thinking that this is a model of all females, you would be right. These 100 individuals, in order for this equation to work, all of these individuals need to give birth. So what we've done by using this equation is we've specified, whether we knew it or not, that this is a female-based model. Later I'll ask you to perhaps change this so this number includes both males and females. But for now, these are females. We open the window, we count 100 individuals, 100 individual females. The window's closed after our census. It's now the middle of the summer, or it's in the late summer, and pronghorns start to breed. They produce 140 offspring. Each of those females is producing 1.4 offspring, although we know that can't happen, but the total result is 140 births. Another assumption comes to mind here now too. Can you think of what that would be? Well, there's a few. One thing that you might have said is every single one of these individuals has to be of reproductive age. Now, after the births occur, we're going to count the number of animals that died. Here we'll use the same sort of equation. It's the number of individuals in our census times the per capita death rate. And we see that there would be 130 deaths. Now you might think of a death rate as being the probability of mortality. And that makes total sense if the number is less than 1. So if you say the death rate is 0.9, that means I have a 90% chance of dying. Here, this number looks a bit odd because the number is greater than 1. What this means is that for every individual in the population at the census, we will see 1.3 deaths per individual that's present in the population, and the result is 130 deaths. I know it looks strange, but what we've done is we've specified not only through these equations when the births happen, but we also specify when the deaths happen too. The deaths happen after the births. All of these individuals are able to reproduce, and the death rate pertains to these individuals as well. At this point, we can calculate the change in the population. So how much has that population changed by? And we signify that with delta n. That's a capital D that's written with a symbol font. And delta n is just going to be the births minus the deaths. And this will tell us if our population is increasing or decreasing or remaining stable. If this number is positive, it means we're increasing. If it's 0, it means we are matching our births and our deaths. And if it's negative, it means our deaths exceed our births and the population is declining. At this point, we're ready to enter an equation into cell B8 that calculates the number of individuals in the population in time step number 1. That's just going to be the number we had in the previous time step. Add in all of the new births and subtract off all of the deaths. And we press OK and drag this formula through, and we see that we need to also drag our births through as well. And now we have our dynamics. Now you might be tempted to try to round these numbers, and that would be a mistake for this particular model. And the reason is because these rates apply to the whole population. And so these rounding decimal places, these half fractional individuals, they actually do contribute to births and deaths in the next generation. That's not a concern for us because we're modeling a whole population. We're not modeling individual animals. What you can do is hide those. We'll turn those into numbers, and we can just shrink the decimal places. That just hides the display of them. It doesn't actually change the number that's underneath of these cells. And if we click through here, we can also get a graph of and look at how the number is changing through time. And we can see that the population is growing. It's every single time step it's adding individuals. And there's something else about this change too. You might notice that at the beginning of the time step we're adding 1 individual. But soon we start to add 2 individuals. And when we get down to the bottom, we start to add 5 individuals or 4 individuals. So the population change is smaller at the top of our series, and it gets larger towards the bottom of our series.